Hello everyone. Can you hear me? Can someone please confirm if everything is okay? Let me make myself a bit bigger at the beginning of this stream. How was the contest, guys? Hard as hell. Oh. Right. How many problems have you solved? Oh, it was pretty hard. Surprisingly hard. Let's see. So maybe let's start this talking about the problems then. I haven't had a chance to read the problems yet, so I was thinking about coming to the live stream and solve it during the live stream. Let's see how it goes. Hello? Oh, that's okay. My voice is echoing? Really? It's not, so maybe the problem is on your side. Okay, so let's start talking about the problems. Let me also. Three friends gathered to play a few games of chess together. In every game, two of them play against each other. The winner gets 2 points while the loser gets 0. And in case of a draw, both players get 1 point each. Note that the same pair of players could have played any non-negative number of times, possibly 0. It is also possible that no games were played at all. You've been told that their scores after all the games are played are P1, P2, and P3. Additionally, it is guaranteed that P1 less than or equal to P2 less than or equal to P3 holds. Okay, find the maximum number of draws that could have happened and print it. If there isn't any way to obtain P1, P2, and P3 as a result of a non-negative number of games between three players, play -1 instead. Well, first, I guess that's the condition for -1 is that the sum of the numbers is odd. If the sum of the numbers is odd, then the answer is -1. And we can also see that in the samples 3, 3, 3 and 1, 1, 1 are -1. But otherwise it is possible, because if some player, we either have two odd numbers or no odd number at all. If we have two odd numbers, we can have one draw between them, and then we have all three even numbers. And then in the worst case scenario, each one of them can win that much from others. Win the half of their score from others. So there is a way. Okay. Yes, this session will be recorded, and it will be on the YouTube channel after this stream, and you can watch it afterwards. Okay, so this is what we can say about -1. It only happens when the sum of the numbers is odd. And when it is even, I guess that each time we can take two of our maximum numbers, and just have a draw between them. if we continue this algorithm, I think the number of draws at the end will be minimum of sum of the numbers divided by 2 and maximum. Sorry. And sum of the numbers divided by 2 if one of them was greater than the sum of the two others, the number of the rows is going to be the sum of the two others. Okay, so I guess S minus maximum. I guess the answer is going to be this. Am I right? Yes, S minus maximum is C, so it's gonna be A plus B. You're right. Minimum of S half and A plus B. Yeah. So you did the same approach then? So yeah, then this is correct. Yeah, sure. I'm just saying that the only condition is that the sum of these three numbers should be even. A plus B, let's call them A, B, and C. And A is less than B, B is less than C. The sum should be even. Otherwise, the answer is definitely -1. Because each time, after each game, 2 points are given. Either both of them are given to the same player or to two different players. Anyway, the sum of the numbers always remains as an even number, right? So A plus B plus C always is an even number. If it is odd, the answer is -1. Okay. And then I say that when we have this, our approach can be like, we want to take the maximum draws out of it. When we know that the sum is even, the sum always remains even as well. The sum always remains even. Why if the sum is even, then we definitely have answer? Because if the sum is even, we either have 2 odd numbers or 0 odd numbers. All of them are even. If we have 0 odd numbers, we can obviously say that the first player wins A half games, the second player wins B half games, and the third player wins C half games. And they can just choose another player, play with them, and win this much. So, there is an answer. And now the question will be that what is the minimum number of draws? But we are sure that there will be an answer. And if we have 2 odd numbers, for example, they are A and B, then we can have a draw between A and B, and then we have 3 even numbers again, and we can have everything like this, right? So this is what we can say. If the sum is even, we always have an answer. So we only need to keep it even. If we keep it even, we are sure that it still has answer. And because each time we want to deduct 2 points, we have A, B, and C. Each time we choose a result for a match and we deduct 2 points. So it always remains even. So the point is the maximum possible matchings that we can have so that we match these points to each other. And we can say that we have that much draws at most. Well, first of all, I can say that this number is going to be at most A plus B plus C divided by 2. The sum divided by 2. Why? Because each time 2 points is deducted from the sum. Each time we are deducting 1 point from one of the numbers and 1 from the other one. Okay. So the answer is at most this much. On the other hand, the answer cannot be more than A plus B. Don't forget that A is less than or even equal to B, B is less than or equal to C. Because it is less than or equal to A plus B, because each time we need to choose at least one of these two. one of these two. This is, for example, A, this is B. Each time we have to choose one of these two. Therefore, each time 1 point will be deducted from this sum. So the answer cannot be more than this. So we have an answer, let's call it x, is less than a plus b plus c divided by 2, and x is less than or equal to a plus b. So we can say that x should be less than or equal to minimum of these two values, right? You wanted to be in discussion? No, you can be in discussion. I just said that if you wanted to stream, yeah, this is something that we decided that maybe it is good that people who have rating master or beyond, if they want, they can stream on this channel whenever they want for the contests. And this is something that you can message me about it and we can talk about it. Okay, so the answer is less than or equal to a plus b plus c half, and is less than or equal to a plus b as well. So we have to take the minimum of these two values, and this is always possible to have this much, because if each time we take the two maximums and just have a draw between them and we continue this procedure, we'll get this much. So yeah, we can, if you want, I can also implement it in a minute, but I guess that's not necessary as well. So maybe we can move on to problem B. Okay. Any book or method I can follow to learn faster? Well, it is better if you try to solve so many Codeforces problem. Is this priority queue solution possible? I did a brute force and each time popped out two elements from priority queue. Yes, that's the exact that's the exact same algorithm, but the difference is that in what we say, you are running the algorithm, but in here, in theory, we find out that how many steps that takes. So yes, we are also thinking about the same approach, but the only difference is that in here it's like we try to calculate that how many times that priority queue will be popped out, but you are brute forcing the algorithm. Both of them work with the constraints. Okay, so the next problem. Today, Cat and Fox found an array A consisting of n non-negative integers. Define the loneliness of A as the smallest positive integer k, such that for any two positive integers I and j, the following holds: ai or ai plus 1 or to a of I plus k minus 1 equal to aj to a of j plus k minus 1. Okay, loneliness is the smallest positive. Okay. For any two positive integers I and j, this should hold. Where x or y did not specify or, in other words, for every k consecutive elements, their bitwise or should be the same. Note that loneliness of A is well defined because for k equal to n, the condition is satisfied. Cat and Fox want to know how lonely the array A is. Helps them calculate the loneliness of the found array. Okay. Let me. Yeah. Yes. Yesterday was very crazy. For B, we say that the or of the whole array, and that's a correct fact. Well, first about dual streams, yes, there definitely be more dual streams. We will have dual with Colin and Sam, but yeah, I'm sorry about yesterday. It was very horrible. We will have that, but yeah, you're right. In each window of length k, the OR of the values in the window should be equal to, in this window of length k, should be equal to the bitwise OR of the whole array. Because if there is any bit that is set in at least one number, there exists a window that that bit is set in that window. Therefore, in all windows it should be set, because OR of all the windows are the same. So we want some k such that the OR of each k consecutive bits is the same. So we need to make sure that every k consecutive elements, its bitwise OR is equal to the bitwise OR of all the elements. You have asked that does binary search help? Yes, binary search helps, but I think we can also do that without binary search too. But binary search works. You can binary search on k. If you binary search on the value of k, then you can just make sure that what is going to be, you need to just find out what is the OR of these values. And in order to do that, you can use prefix sums. How? You have 30 bits. For each of the bits independently, you can keep that how many of that bits do you have in any prefix. And then you need to have a for on all the bits that they are set in the whole array. I mean, in the whole array, there is at least one of them. You can use prefix sum to check that out as well. And then see that if in this subsegment they exist as well, using your prefix sums. But there's also another solution that I think it works. And that is like this. For each bit, we have 30 bits, because all the numbers are less than 2 to the power of 30. For each bit, try to find all the numbers that have that bit on. And then see the distances between each two consecutive of them. And take the maximum of these values. And after that, take the maximum of these values for all the possible, for all the bits. So we have some blocks. These will separate everything into blocks. And see that what is the size of these blocks, and calculate the maximum of them and report the maximum of them as your answer. Yeah, why I said 30? Yeah, it is 20, sorry. 20. But I think it also works for 30 as well. I mean, we don't have any difficulty if AI was up to 2 to the power of 30. Right? Do you agree with this? Has anyone used this approach? Yes. I'm just saying that for the value of k, the bitwise OR of each k consecutive elements is the same. Okay. The bitwise OR of each k consecutive elements is the same. Okay. And they should be equal to bitwise OR of the whole array. Why? Why it should be equal to the whole array? Because for each bit that is set in one of the elements, there exists one sliding window that this bit is on in that. And because the bitwise OR of all the windows, by window I mean k consecutive numbers. I call this a window. In each window, there should be they should have the exact same bitwise OR. So when in one of them that bit is set, in all of them that bit should be set. So all of them, the OR of all these k consecutive numbers, OR of all of the windows is equal to OR of the whole array. So if for any bit that at least in one number that bit is set, we know that in every k consecutive numbers there should be one of that. Okay, and so we can have a for on all such bits, and then try to find all the numbers that have this bit on, and then we have several blocks. I say that k should be greater than or equal to this value, I mean the first index. It should be greater than that. greater than or equal to this value, this length, greater than or equal to this length, and also greater than or equal to this length, because in the last interval this should lie. I mean, this element should lie in the last interval. So k should be greater than or equal to the maximum of the distances between each two consecutive elements that have that bit on, and the index of the first element, which shows you the size of the first block, the minimum size for the first block, and n minus the last one. Okay, and plus one if you use one-base indexing. Anyway, you can see what is the appropriate size for the last segment. And then this way you take the maximum of all these numbers, and that is gonna be your answer. Yes, we are checking for, no, we are not checking for every value of k. We are checking for every possible bit, and we just find the value of k. How? I'm arguing that the value of k is gonna be equal to the maximum of all these values. For example, we are at bit 0, and there are several numbers that have bit 0 on. Then we know that the answer should be, the value of k should be greater than or equal to all these lengths. So it's enough to find the length of all these blocks and take the maximum of them, right? No, our approach is not a sliding window. Our approach is that we iterate over all bits, and then we iterate on all the numbers, n numbers that we have. So we have log of maximum a times n and then when we see that a bit is on, we save that for example this bit, which numbers have that bit. And then we take the maximum of distances between each two consecutive ones and the distance to the first, from the beginning to the first one, and from the last one to the end. We take the maximum of all these numbers, and we say that this is equal to the value of k. Yes, I can show you code. Do you want me to just show the code or implementing it? Let me show you this code. For example, in this one, we get all the numbers, our answer is initially 1, then we have a 4 on all the bits, and then we have a 4 on all the numbers, and yes, that's exactly what we said. If this number had this bit, ans is equal to maximum of ans and I minus last, I mean the last number that had this bit on. And at the end, if last was not equal to -1, ans is equal to maximum of ans and n minus last. So yes, this way you can easily find the maximum possible size, the minimum possible size for k. It is equal to maximum of all these numbers. Okay. Oh, that's bad. That's bad. I hope that you get back soon. I mean, in CF. That's okay, that happens. These things happen, and it's important to start again. How can this problem can be solved by newbie? We have to add +1 to range, right? No, in this problem we do not have to add 1 to a range. We just take the maximum of these values, distances between each two consecutive numbers. Okay. So yes, this is gonna be how problem B can be solved. Do you have any questions about it, or shall we move on to problem C? In this problem, yes, binary search could also be used, because you could also have a binary search. Then you will have times log n as well. So you will have n log n times log a. Yes. I summarize B again. First, I said that for fixed value of k, we can say that for fixed value of k, the bitwise OR of each k consecutive numbers should be equal to the bitwise OR of all the numbers in our array. Why? Because for every bit that is 1 in at least one element, in at least one window, that bit is on. In at least one interval, that bit is on. Therefore, because all of them are equal, in all of them it should be on. So the bitwise OR of each interval should be equal to bitwise OR of all of the numbers. The bitwise OR of all of the numbers. Okay. And then I'm saying that we need to choose our value of k such that always for every bit, every bit that it is on in at least one element, there will be at least one element with that bit in every window. Every window should have at least one element with that bit on. And therefore, we can say that when we find all the numbers, elements with that bit on, we can just find the distances between each two consecutive ones and the distances to here and to here. And we need to take the maximum of all these values, because these all give us a condition on the value of k. For example, we know that k should be greater than or equal to this size. It should be greater than or equal to this size. It should be greater than or equal to this size. And it should be greater than or equal to this size. Otherwise, if it is less than that, then we have a choice to have a window that does not have this bit on. Right? Yes. I will find the differences between one's font. Problem B seems like yeah, maybe 1400, 1500, I guess. Yeah, around 1400 maybe makes sense. Like if we are able to set all bits in a subsegment, then we again check for the next subsegment in which all bits are set again, and then is the max of all these windows. Yes, it's like there are all conditions. There are all some conditions for the size of our sliding window. That there are all conditions for that size. All of them say that, yeah, the size should be at least this much. About why is the range a monotonic function? The reason, and you have said that implement BS1s and let's solve C. Yeah, okay. So maybe it's better if I don't implement this problem to talk about C as well. But let me explain it again so that make sure that everyone understood it. Why binary search is monotonic? The reason is that we said that for every window, the bitwise OR of every window should be equal to the bitwise OR of all the numbers. Do you agree that when we extend the size of the windows, their bitwise OR will not decrease? Since it will not decrease, we know that if it was equal to the bitwise OR of the whole array, it is still equal to the bitwise OR of the whole array. All right. Oh, okay. Yeah, maybe you need to start. Yeah, that happens, that sometimes you can't accept a problem in the contest. In order to improve, I strongly recommend you to upsolve and try to solve the problems that you haven't solved in the contest afterwards. For example, you found difficulty in solving this problem, implementing it. Okay, now after the contest, make yourself to do it. And as you can see, there is also a very easy way to accept this problem. I mean, using just this code, you can accept it. So it is possible. And just if you want to improve yourself, you have to do this after the contest. That's the point. That is completely okay. That sometimes happens that you can accept some problem in the contest, but you can easily absolve that afterwards, and that really helps you to improve. Do you have any other questions about problem B? If you try a brute force solution, checking bit was or for all the numbers with a sliding window that checking bit was over all the numbers. If you have a binary search on k, yes, you can do that. But if you don't have a fixed value of k, it would be hard if you're going to increment it one by one. So yeah. Okay, sure. I'll solve problem C now. Cat, fox, and double maximum. Fox loves permutations. She came up with the following problem and asked cat to solve it. You are given an even positive integer n and a permutation p of length n. The score of another permutation q of length n is the number of local maximums in the array a of length n, where ai is equal to pi plus qi for all I from 1 to 1. In other words, the score of q is the number of I such that I is between 1 and n, and the ai minus 1 is less than ai, and ai is greater than ai plus 1. Okay, find the permutation q that achieves the maximum score for given n and p. If there exist multiple such permutations, you can pick any of them. Okay, so you have a permutation, we want to add another permutation to it so that the number of local maximums will be maximized. Well, okay. Okay. Well, yes, this problem seems like more like a more challenging one. Do you guys have any idea? Has anyone solved it? Maybe. Yes, let me see what is the constraint on n. N is up to 10 to the power of 5. I'm sorry, I received a message just now and I was distracted for a moment. Okay. So we want to maximize the number of local maximums. Well, it doesn't seem trivial at least. We select. Okay. So you argue that you can always alternatively set local maximum. So you say that the answer is always n half or so. Okay. Okay, let's see. Let's see what we can say on this. So we want to make sure that what we argue seems like we can prove that from every two elements, one of them can be local maximum. From every two consecutive elements. So the answer is gonna be this way. The answer is gonna be n minus 1 divided by 2. It is dependent on if we want to change even indices or odd indices. Grab all even or odd indexed elements and the sequence with the bigger elements. We want to increase those by n half to n from smallest to biggest in that sequence, because if we have at even indices 6. Yeah. Yes, when we find out. Okay, I see. Okay, first, for number 1, we know that it cannot become greater than any other elements. Even if we add n to it, I mean, how do you say that? Okay, assume that, for example, our number 1 is in here, for example. Well, first, yeah, it is obvious that we try to maximize these numbers and minimize these numbers. In order to maximize these numbers, we know that we need to add numbers, for example, between n half and n to it. There's some plus 1, minus 1 in here, but the general idea is that we want to add the greater numbers to these numbers, and the smaller numbers to here. Right? And okay. Okay, and then this way we know that these numbers are added by, compared to these ones, are around added by n half more than the others. Let me maybe show it on a code. Maybe this would be a better thing. I mean, it would be more definite. Let me see. First we set all the numbers to be n plus 1. Okay, so they are all equal. They are all equal to n plus 1. When we set b of I equal to n plus 1 minus ai, they are all equal to n plus 1. And we set all of them. We insert all of them in our set. And then we have a for if set that upper bound of b of I is equal to, let's see, that's end continue, else x equal to Okay. So we start from elements number 2 and we move forward. In here we are just checking if we can make this number larger than what it is already. We want to try to make this number larger than what it is already. So in order to do that, we just check what is a number greater than b of I that currently have, and we will swap this number with this one. So we want to make this number larger, greater, so we find a number greater than its current value of b of I and we swap it with this value. And then erase this one from our set. And then we have an additional I++ because we want to skip the next number. For the next number we don't want to do anything. Right? So this way we move forward, and each time if we can make a number greater, we will do that. Otherwise, if we cannot do it, we just skip it. Instead of, I did it in the same way, but instead of upper bound, I just used an array and sorted it. Yeah, that could also work because this is offline, kind of. And you could just, instead of erasing something from your set, you could just maybe mark it or something. But still, you need to have an upper bound. And find out in a range if any of those numbers are available yet. Right? Okay. So yes, the core idea in here is that first we try to prove that out of every 2 consecutive numbers, we try to make one of them as a, we want to set at least one of them as a number that has this condition, such that AI is greater than A of I minus 1 and A of I plus 1. So we want to reach somewhere near n-half. Okay, this is the intuition. First, we say that the answer is gonna be somewhere around the value of n-half. Okay. And then we start from the second element. Our approach is this. We do a greedy approach. This is our approach. We do a greedy approach at all. We start from the beginning. In here we see that we started from the second element and until less than n, until n minus 1. And this is one list. We try to make it a local maximum. If we can, great, we make it great, a local maximum. If we cannot, we just skip it. Okay. So when we try to make it a local maximum number, we just first, initially, we set all numbers. We set bi equal to n plus 1 minus ai. Then bi is a permutation. And we know that ai's will be all equal to n plus 1 this way. Okay. I'm sorry, I keep receiving messages and I get distracted. So we have n plus, we have all of them equal to n plus 1, right? So now when we start from the beginning, each time when we want to find it, make it a local maximum, we know that the number before it is equal to n plus 1 or it is less than n plus 1. It is possible that it is swapped with something else. For example, when we are in here, it is possible that the previous number is swapped with a greater number before, because we know that if something swaps, if some other element swap its own value with you, your number will become smaller. Okay. that number becomes smaller. So we know that the previous number is at most n plus 1. So we know that this one is also n plus 1 right now, and we want to make it greater than what it is already. So we need to find an upper bound for the value of b of I, and then we search for that. We find the first number greater than the b of I, and we swap these two. And after we swap them, this number is going to be greater than n plus 1. So it's going to be greater than the number before it and after it. And then we add 1 to I again. And this way we can have all the numbers at the end. Does this make sense? So the idea is that we try to greedily make all the numbers maximum possible. I mean, local maximum. Make maximum possible of local maximums. That is the whole thing that we want to do. And yeah, the time complexity in this approach is n log n. So we start from the beginning, we go forward, and greedily each time we try to make the current elements a local maximum. And in order to do that, we try to swap the number with a number greater than itself. And then we erase this number from our set because this number is not available anymore. And this was the minimum possible value greater than this number. So we try to sacrifice a number which is the minimum possible. Okay. And then we go forward. Yeah, we have bi equal to n plus 1 minus ai initially, because initially we set all the numbers. Initially, the first thing that we do is that we set all the numbers to be n plus 1. We want ai to be an array that all of its elements are exactly n plus 1. All of the elements of ai becomes n plus 1. How? We set b of I equal to n plus 1 minus ai. So these are just some guiding values. We know that bi is initially just set as a guiding value that is a number that makes that element equal to n plus 1. Okay. And then as we move forward, we try to make the element greedily, we try to make the current element a local maximum. In order to make it a local maximum, we know that the previous number is at most n plus 1 and the next number is at most n plus 1, because initially they were n plus 1, and even if some other element swapped their value with these ones, it makes them smaller. So now they are at most n plus 1. So if we just make this number greater than n plus 1, then we're done. Then we have a local maximum. And how can we do that? It is just enough to find in our set the first number greater than the current bi. We need to find the first bi greater than our own self, and swap our value with this. Yeah, lower bound is just in order to find if we can make this element greater. Does this make sense? So we greedily move forward, and each time we try to make our current element greater. Yeah, sure. We can also check another code and talk about that one. So for example, this one. In this one, let's see what this person has done. I think this one is closer to what you guys said in here. See, in AI, bi is initially 0 in this one, ip of ai is equal to I. Okay, if IP of I modulo 2 is equal to IP of 1 modulo 2, B of IPI. So this one is closer to what the guys in chat said. This code is trying to see that where number 1 is, and try to make all the numbers in a different index a local maximum according to them, according to the position of elements number 1. Okay, according to the position of according to the position of the first one. Why there is an I++ in the else? In that one, because we wanted to skip the next element as well. 4 itself had one I++, there was one additional I++ there, so that we also skip the next element. That was the reason for I++ there. Can you provide an editorial for this post stream? What do you mean? You mean a text-based editorial? About this one, I just it just finds all the elements with index 0 indices different to with parity different to the index that has value 1, and it tries to give them the maximum number starting n, and the rest of them gives maximum number starting from n½ to them. And this way it is trying to find the answer. But why it is always greater than the others this way? Why are them going to be maximums? How can we prove that? How can we prove that they are going to be greater than the elements next to them? Text-based, yeah, I guess that I cannot do that. I think that I don't have the time to prepare that, but if there is any volunteer who might do that, that would be perfect. And I can share that wherever. I can share that in the Discord server, in the YouTube channel, everywhere. So if everyone is interested in providing that, that would be fine. But also I guess that the editorial will be posted on Codeforces very soon too. If it is not posted so far, it's not, but it will be posted here in contest materials. Yeah, I have a Discord server. We have a Discord server. You can join if you want. Guys, can one of you send the link of the Discord server? Because I don't have access to it right now. If someone has access to it and can send the invites link of the Discord server, that would be great. You got it? Okay. If you got it, please share it in here as well, so that if others wanted to join, they can do it as well. Okay. So I just trying to make sure that why this should be necessarily true, because maybe the element next, I think I guess that I got something wrong, because maybe the difference between two adjacent elements is a lot more than this, that even if you add n to it and n½ to it, this will be still greater. I mean, you add n to it and n½ to it, for example, but this one will be still greater. Why such things? Why such a thing never happens? IP of I. Oh. Oh. I think I see now. Okay. Yeah, it makes sense. Yeah. Yeah, it tries to, there are several elements that we want to maximize, and there are several elements that we want to minimize. In order to maximize an element, we see all the elements that we want to maximize, and we start from the least one of them, the one of them, from the one that is smallest between them, and try to maximize that one. If you see in here, we start from 1 and go to n, and we work with IP of I. What is IP of I? Is the index of the element that contains the value of I. So I is the value, not the index. I is the value, IP of I is the index. So IP of I is where I is in. Okay? IP of I is where I is in. And because we start from the smallest number and go to the greatest number, we give a greater number as bi when the number itself is smaller. And when we do that, we know that for each two consecutive elements, if such a thing happens that this is a lot greater than this one, this number will be added by a small number because it is too large. And this one will be added by a number a lot greater than that, and it would become greater than that one. And the reason is we know that as much as we make this number greater, the number that will be added to it will become smaller. So we can find the bound for all these numbers. And this way we can argue that these numbers, all these numbers in maximal positions will be greater than the numbers in local minimum positions. I see, no problem. Yeah, that happens. For me as well, it was exactly like that. When I started, that was exactly like that. So it was taking me an hour to solve only the first one. But the important thing is that you continue training and then you will grow. Yeah, but exactly the same thing happened for me. I always show my plots. Yeah, in here, I was a newbie. Such thing happened to me. Maybe we can even view my performance in such contests. You see that 41 minutes to solve a problem A, and 5 wrong answers, and I was a newbie. But I guess only 2 or 3 months after that I had this contest, which was my best contest at the time. I ended up in the 4th place back then in this Div 2 contest. So it happened only after a few months of training hard. So if you train hard, this can happen. Yes, I plan to discuss problem D as well. Are you okay with this problem? IP of I modulo 2 not equal to IP of 1 modulo 2 means that the indices of these two we know that we see that in which parity number 1 is. Number 1 is in an even position or in an odd position. If it is in even position, we try to maximize odd positions. If it is in odd position, we try to maximize the even positions. So this is how we will move on. And that is why we compare its index with the index of number 1. And this way we can maximize those numbers that are not in the same parity. The indices are not in the same parity with number 1, and just maximize them. This line is for that. Yep. So is it okay? Shall we move on to problem D? If you have any question about problem C, you feel free to ask. Otherwise, problem D states that this is an interactive problem. Fox gave cat two positive integers n and k. She has a hidden array a1 to an of length n such that ai is from 1 to n for every I. Now they are going to play the following game. For any two integers L and R, such that L and R are between 1 and n, define L and f of L and R equal to R minus L plus 1 times maximum of A of x between L and R. In other words, f of L and R is equal to the maximum of subarray multiplied by its size. Cat can ask Fox at most 2n questions about the array. He will tell two integers, L and x, and she will tell him one integer p as the answer, the smallest positive integer r, such that f of L and R is equal to x or n plus 1 if no such r exists. Okay, now cat needs to find the largest value m, such that there exists a sequence c1 to ck minus 1 such that it is in ascending order, and f of 1 and c1 is equal to f of c1 plus 1 and c2 to f of ck minus 1 plus 1 and n equal to m. If no such m exists, he should indicate this and take minus 1 as the answer. Note that for k equal to 1, m is always equal to f of 1 and n. Okay. Okay. In other words, the goal is to find the largest m such that you can split the array into exactly k subarrays. K is the constant given to you in the beginning of the interaction, so that all the subarrays have the product of their length and their maximum equal to m, or determine no such m exists. Every element should belong in exactly one of the subarrays. Cat doesn't know what he should do, so he asks you to play the game for him. Okay, so we want to fix. Awesome, Dimitri. If you had any idea, if you solved it, you can say your idea in here. So we want to fix some value of k. We have a fixed value of k. I want to split our array into k parts such that each part has their value of L equal to m. So I think the most efficient thing that we can do is to start seeing some people code. Let's see Rainbow's code and see what he has done. Try to find out what he has done. He says that we have values, we get the values of n and k underline for a equal to n, a. Well, the query function is just something that's you give it, you just print f the query and just gets the answer and return it. So this query, it is just for making the code more neat. That's just it. So if query of 0 and a times n was equal to n, break. Let me see. Okay. So yes, first he tries to find the maximum, as Dimitri is also mentioning. This is the maximum. Only for maximum this happens. When query of 0 and a times n is equal to n, it means that the first place that the interval starting at 0 will be ended such that the value of f will be equal to a times n is n. So it means that if you consider the whole array, starting from 0 and finish at the end, the value of n, the f of it is equal to a times n. So it means that the maximum was a, right? Because we said that the result of query was n, so the end of the interval was n, and the start of it was 0. And the answer is a times n, so the maximum was a. Do you agree? Yeah. So first, we find the maximum. And we wanted to split into k parts or k plus 1 parts. No, exactly k parts. We want to split into exactly k parts such that in each of the parts, the value of f is equal to n. Yeah, so then we start from n over k and we go downwards, I equal to 0, k equal to 0, while I is less than n and k is less than k underline. I is equal to query of I and a times c. Okay, so what is the value of c? Maybe that's the first. C is gonna be the length, I guess. Yes, c is equal to the length. Oh, well, I is less than n and k is less than k underline. Okay. Oh. Oh, that sounds very neat. Yeah, that was very neat. What do you recommend on doing little Codeforces first? Well, first I recommend you to start on Codeforces. That's for competitive programming, mostly not LeetCode, and sort the problems and try to solve them from the beginning. But about this solution, it was very neat. I really liked it. First, this was very beautiful. First, it finds the maximum, which is value a. It finds the maximum, which is value of a. So now we have the maximum. So we know that value of m should be a multiple of a, because this maximum is the maximum value in at least one window, in at least one part. This is gonna be the max. For example, maximum is in here, then in one part, it is gonna be the maximum. Okay? So in one part, it is gonna be the maximum value. So whatever the length of it is, for example, if the length is x, m is gonna be equal to ax. So m is a multiple of a. We are sure about that, right? Now the question is that what is this multiple? What is this value of x? Are you okay so far? If you're okay with that, put a plus please in the chat. I want to make sure that everybody is following and everything is clear. So I'm just saying that m should be a multiple of a. M should be a multiple of a because a is our maximum and it's gonna be the maximum in at least one part as well. And whatever the length of that part is, for example, if it is x, or let's call it c. Let's call it c. Whatever the length of that part is, let's exactly like the code, call it c. M is gonna be equal to ac. What about the rest of you? If the rest of you are okay, please put a plus as well. And if you're not okay, ask questions or just put a minus and I will repeat it. So m is equal to a times c. And what do we know about c? About c, we know that c can be at most n over k. Why? Because we have k parts and this part has the maximum. has the maximum value. It has the global maximum, so its maximum is also maximum over all the parts. So it is a global maximum. So its length can only be less than or equal to average length. We know that the average length of the parts is n over k, and because the maximum of this part is the highest possible, this should be less than or equal to the maximum possible length, the average length, sorry. So we know that we have k parts, so the average length of them is n over k. So when we know that the average length is n over k, we can say that this window has the highest possible maximum. So its length can be at most n over k. So I can state that C is at most n over k. That's why it starts from n over k, and he has called k as k underline in here, and C minus minus. And now we check if everything can be fine. We start from the beginning, and each time we query I and A times C. We know that M is equal to A times C, as we see in here. Let me just... as we know in here, M is equal to A times C. So all we can say is that each time we query it, and then we say k plus plus. And we do it while I is less than n and k is less than k underline, which is the main k that we have. And if everything was good, we have our answer and we break. If everything was not good, we check the another C. We know that inside here, this while takes O of k. Because the number of groups is equal to k, and each time we add one group. And this for has n over k iterations. So in total, this part is gonna be O of n. And that's also so beautiful. So we have a 4 of length n over k and a 4 of length O of k, and a while of O of k iterations. So that's gonna be all. Is it clear? Do you have any questions about this, or is it clear? This was really an interesting problem. Yes, sure. I'm just saying that first we calculate what is the maximum. We find the maximum first. And after we found out what is the maximum value, it is just enough to say that when we found out what is the maximum value, we know how to find the maximum value. We just need something that's the query of 0 and A times n will become equal to n. Then it means that the answer for the f of 0 is equal to n. Then we know that the f of 0 and n is equal to an. So it means that a was the maximum. So first we calculate the maximum. Afterwards, we say that this maximum lies in at least one part, in a part. This maximum will lie in a part. Assume that the length of that part is c. Then m is equal to a times c. And we know that c is at most n over k because this part has the maximum, the highest possible value for the maximum. So its length is the least possible amongst all the parts. And because the parts in average have the length n over k, we can state that c is at most n over k because this interval has the length at most as the average value. And therefore, we can just state that in here. We can just state that we fix the value of c, and then we have a while. We assume that this is going to be our m. Each time we query I and the value of m, which is a times c, and if it was somewhere, we just say k plus plus, and we go there. We start our next partition part from there. So we start and go forward, and if we see that we can make this happen, I mean make this m happen, and if it was possible, then we report it as our answer. Otherwise, we just try the next value of c. If none of them works, then there's no choice. There's nothing that we can do. Okay. There's not some specific algorithm, but the idea was very interesting. I mean, this was a beautiful problem in my opinion. Yeah, you're welcome. In my opinion, this was a very beautiful problem. I really liked it. Okay, awesome. Guys, do you want me to also explain problem E? I mean, does anyone need problem? If you want, if any of you want, we can also explain it. We can read the codes of that one as well. Just tell me if you want that as well, if anyone wants that as well or not. If no one wants, maybe we can stop the stream for today, but if you want, we can talk about it. So, do you want to talk about it? Okay. Is C easy or not? C was not very easy, I guess. No. And it has some yeah, I don't think it was easy personally. As a problem C of diff 2, I don't find it easy. I think C of diff 2 is usually even easier than this, way easier than this. Alright, I see. So you solved A to D, Dimitri, right? Okay, let's also talk about problem E. Fox has found an array P1, P2 to Pn that is a permutation of length n of the numbers 1 to n. She wants to source the elements in increasing order. Cat wants to help her. He is able to swap any two numbers x and y in the array, but only if x plus y is between L and R. Okay, it is imposed on the values of the elements, not their positions. He can make such swaps any number of times. They don't know the numbers L and R yet. They only know that it's true that L and R are from 1 to 2. Okay. You are given the number n and the array P1 to Pn. Determine how many pairs L and R satisfying the condition are there such that you can sort the permutation if you can only swap numbers x and y with this condition. A permutation of length n is okay. So you want to find the number of pairs of L and R with this condition such that you can source the permutation. Interesting. The problem seems like interesting. Let me bring a code and try to see what people have done on this problem. Okay, this code is from an LGM. Right. Right, I see. So in this problem, first you get the queries and you get the number of queries, the number of test cases, and then each time scene n. uh, if ai not equal to I, okay, so we have all the indices that they are not equal to what they should be equal to. For example, we have in here that if a of I is not equal to I, then there is something that it shouldn't be here. Then mn is equal to minimum of mn and I, mx is maximum of mx and I, s that inserts I plus ai. Okay. If s dot empty, if s does empty, then the answer is all the pairs. So the answer is going to be the sum of the numbers from 1 to 2n. Otherwise, we start from maximum plus 1 between all the indices. In here we stored the numbers that are not in the positions they have to be. So when we know that in AI, I is not at AI, so I is an element that should change its position. So we are at I, and we see that AI is not equal to I. So I is not in its position. So we save the minimum such I and the maximum such I. And we insert I plus AI there. And then if s dot empty, the answer is trivial. Otherwise, we have a 4 of I from maximum plus 1 to 2n. I guess this is our R. I is the value of our R, I guess. Then int of L is equal to minimum of I minus 1 and mn plus n. Wait a minute, where s is used other than here? I mean, this code just needs the size of s. S seems like s is not used anywhere, just the size of it is used. I mean, the values of it, I don't find anywhere that the values of s are used. Oh, I see. That is maybe because if two numbers had equal number of I plus AI, which only happens if we have only two elements to swap. Anyway, we are fixing our R, we try to fix our R. We say that R should be at least our maximum plus 1. Why? Because we know that mx is not in its correct position, and we know that at least it should be able to be swapped with 1. So because it should be swapped with something. So R is definitely greater than or equal to mx plus 1. But the question in here is that why L is equal to minimum of I minus 1 and mn plus n. Why L is going to be equal to minimum of these two at most. Well, obviously L cannot be greater than I minus 1. Why L cannot be greater than mn plus n? That is also obvious. It cannot be greater than mn plus n because mn should be swapped with something, and the greatest thing that it can be swapped with is n. So obviously L also should be less than or equal to mn plus n. Why? Because mn is not in a correct position, and it should be swapped with something. The greatest number that it can be swapped with is n. So at least it should be able to be swapped with n. So yeah, that's like it. But yes, that is necessary. Now the question is that why it is sufficient. No, swaps do not always use one, but these are just some conditions. We are sure that at least it will be one. Both of the elements are at least one. So our value of r, if we're gonna swap mx with something, our value of r should be at least mx plus 1. And if we are gonna swap mn with something, the value of L should be at most mn plus n, because this sum of these two is at most is at least mn plus n. Right? At most mn plus n, sorry. So L should be less than or equal to that. Cannot be greater than that. But the question in here is that why all of them are sufficient. Let's for a second forget about this line, and we'll find out how that's useful. Oh. I guess that line is for the, okay. I guess that line, I guess that in here, he tries to find all the values for L less than R, and this case is only for when L is equal to R. It just says that if for all of them the sum of I plus AI was the same, we can have L equal to R equal to these values of I plus AI. So in this for, we are trying all the appropriate values pairs for L and R such that L is less than R. Maybe we can swap. Oh, thanks. Maybe we can swap n into the place where mn should be. Yes, but anyway, we are saying that if we are gonna swap mn with anything, the sum of mn and that element is gonna be at most mn plus n. So L cannot be greater than that. Otherwise, we cannot swap mn with anything. And because mn is not in the correct place, then we cannot do anything. And do not forget that these mn and mx are not positions, they are numbers. In here, we know that ai is not equal to I, so we need to move number I. Because we need to pick it from wherever it is and bring it to ai. Right? So these are numbers, not indices. These are the values. If you see in here, note that the constraint is imposed on the values of the elements, not their positions. Okay. So, yeah. So these are the values for L and R, which L is less than R. So now the only thing that we need to say is that this condition is sufficient. It is necessary, it's trivial that it's necessary, but how can we say that it is also sufficient? How can we say that it is also sufficient? Let's think about that. Oh. Oh. Let me see. Great. Yeah, that's awesome. Yeah, this is very interesting. Because L is less than R, there are at least two possible sums that we can have. Okay. Now assume that L is less than or equal to mn plus n. This was fantastic. L is less than or equal to mn plus n. Then mn can be swapped with n. But because L is less than R is greater than L, n can also be swapped with mn plus 1. Right? And mn plus 1 can also be swapped with n minus 1. And n minus 1 can also be swapped with mn plus 2. It's like we have a permutation and we can swap every two adjacent elements. It's like these are adjacent and we can swap them as we want. And everything between mn and mx are going to be connected this way. And we can easily swap all of them as we want. We can make any order between mn and mx. mn can be swapped with that's why L less than R helps us. L is less than R, so mn can be swapped with n. N can be swapped with mn plus 1. Mn plus 1 can be swapped with n minus 1. N minus 1 can be swapped with mn plus 2, and so on. So these are all connected. All the numbers between mn and mx are going to be connected. Does this make sense? We can also say the same thing with mx and 1. And we showed that if we only have these two conditions, then we can permute all the elements in the wrong orders in any way that we want. Therefore, we can sort all the elements. And this line is only for the case where L is equal to R. How, if all of them have the same sum of the values, I mean for all of them, I plus AI is the same exactly, each time we can swap two of them, we can set L and R both equal to this value. We can set both of them equal to this value. And then we can swap each two of them. We know that I is AI. At position I, we have AI. And also, we are sure that at position AI, we have I. Because the sum of the values in the incorrect positions are the same. So at position I have AI. At position AI, I have I. So I can just swap these pairs. And I can set L to be equal to R. That's why in this specific case, I say ans plus plus. And then I see out ans. This was incredible as well. I really like this one too. The theory parts in this one, in this part was beautiful. Okay, is that was that understandable? Does that make sense? If you have any questions, you might ask about it. If you want to talk also about problem F, you can say that in here and then we could discuss F as well. Otherwise, we can stop here. This was interesting. Yeah, guys, for a long period of time, all I was doing was trying to read codes and understand them. After a while that I thought enough on a problem, if I wasn't able to solve them, I was reading people's codes and trying to understand what they're doing. And that helps me a lot, both in terms of trying to find out how to implement things and forming my intuition about the problems. And yeah, that's why I strongly recommend doing that. Okay, do you have any questions about this one? And is there anyone who wants a discussion for problem F as well, or not? Feel free to ask any questions or anything. Does anyone want problem F to be solved as well? Let me also take a look at the final ranking. Oh, only 6 people have solved the last problem. The top 6, only the top 6 have solved the last problem, and in total 17 people have solved problem F. Interesting, really. And between the official participants, one has solved. It would be interesting to see who was that person. Yeah, so, and the ratings are updated too fast. It's weird. Okay, guys, if there are no other questions, etc., then I think we can meet next time. Maybe tomorrow I will also stream the beginner contest. I'm not sure if I'm available, but even if I'm not, maybe someone else will do that, and we'll discuss that contest. Maybe Ahmed or Yan or someone else. Yeah, thank you very much for joining. It was really great to have you here again. I'm happy that we're having more streams now. And sorry again about last day. I really have no idea what happened. I think something was wrong with me. I was definitely something was wrong with me, and I don't know what. But we are gonna do duel with Galen, Colin, and Sam, and also with other great competitive programmers. We're gonna have some duels. We're gonna have a lot of fun to do, especially in the summer that we are freer. So yeah, I guess I'll see you next time, guys. Thank you very much for watching the stream till the end. It was so nice having you. See you the next time. Bye.